So first of all, my name is Vivi. I work at Hugging Face. I do open source audio. And a lot of what you're going to see today is essentially optimizations we bought on top of Whisper. And yeah, let's see how it goes. We would most likely have time towards the end to have Q&A. If not, then I'll be around just so that you know. All of the stuff that I'm going to present is also on my GitHub. So you can follow along if you have a laptop as well. All of these are self-contained Colab notebooks that you can just run and should work on free Colab GPU as well. All right, let's go. So who here knows what Whisper is? All right, nice. You make my job easy. So Whisper was this model, a speech-to-text model released by OpenAI. Pretty much the only good thing they did in a while. So essentially, it's an encoder-decoder model, meaning it takes audio in and it gives you a sequence of text out, right? So you throw in some sort of audio, it detects what kind of language that audio is in, then it would transcribe it in, whatever language it thinks it is in, and you get the output. It is a very basic transformer type model. So essentially, it follows the same sort of architecture which was Fani et al. Sort of put out there. What makes it special is that it was like the latest version of Whisper, which is large V3, was trained on 5 million hours. And that's a non-trivial amount of audio, which means that it has seen a lot of languages. It has, it essentially has been trained on internet scale data. So it generalizes quite well across languages, and so on. It is multilingual, so I think from our analysis, like it supports up to like 120 languages, pretty much all of European languages. It supports, as well as low resource languages. Like in my case, I'm from India. It supports Hindi and also like some southern languages as well, and so on. It's quite reasonably good. And at this time, it is currently the state of the art, has been for like past 1.5 years. So it makes it worthwhile to optimize it. So in the slides, I've put in references in case you want to learn more and like read the paper and so on. There's also a link to a demo over here. In the interest of time, I'm not going to go in and play around with it. But in case like you want to do it, you can just click on that and you can play around with the demo. Now there is like a question, like we're talking about how to make this fast, how to make it as fast as possible, and so on. But the real question is, why should we make it fast in the first place, right? So first of all, it is a big fat model. It's a 1.5 billion parameter model, which makes it non-trivial to run for real-time use cases, right? So if you want to transcribe, as I am saying right now, it would be very difficult to do that in real time. Meaning, as I'm speaking, it would be very difficult to transcribe it word for word. So it's good to optimize for that. Second, of course, like as I said, real-time transcription. Third, to reduce inference costs. Like all of these models, you cannot just run them on CPU, so you need a GPU at the end of the day, and so you want to optimize costs, right? So instead of running it on let's say like an A100 or an H100, you want to run it on a T4, or you want to run it on like more like lesser capacity sort of model, GPU, and so on. Last but not the least, it is fun to optimize models, let's be honest. And yeah, so now that we have established what exactly are we going to do, how exactly are we, like what all possibilities are there to optimize such a model? So I'm going to be covering like a small subset, not the entirety of optimizations. And I would, towards the end of the slides, I would leave you with certain other ideas that me and my team are currently trying. And you can join along with it. All of our research is open source. And yeah, hopefully we'll have some fun along. I won't get into the details of what exactly they're doing just yet. But as I go through the slides, like all of this would make more sense. All right. So we know like we're gonna try out say 5 or 6 things, but how exactly would we measure how good the model is whilst we're optimizing it, right? So we're gonna start with we're gonna have a very simple table. We're gonna have a bunch of different methods, and we're gonna see how much time it takes to transcribe 10 minutes of audio, right? Very simple, easy peasy. That's it. And just a quick note that unless I state otherwise, all of these methods do not incur a loss in performance. Meaning like these are like, these would pretty much always give you the same result as if you were running an unoptimized model, right? Cool. So let's start with the first one. It's FP16. So just by the nature of how models run within PyTorch, by default, they run on FP32. Meaning they run in full precision, which is highly unoptimized, but it is the most accurate representation of tensors, right? So as you do a forward pass, you would get the most accurate transcriptions from it. But that means that you pay two things. So you pay the memory cost, and also you pay the inference cost, because your overall sort of matmults, so like your matrix multiplications across all the layers, would be even more time consuming. So about 2 to 3 years back, PyTorch came up with floating point 16 kernels, which essentially allows you to with negligible loss of performance, or zero in most cases, you can just run inference or training just in floating point 16, right? Which is great, because you pretty much run everything in half precision. So you just you do inference 2x faster, and you reduce your memory sort of cost by half. So yeah, so it's 2x as fast as floating point 32, zero to negligible loss in performance. This is tried and tested. So pretty much like everything that you see out there is floating point 16. That's why this is our base case. So we start off with like FP16. I don't want to start with like FP32 bullshit, just because like people say that, yeah, like, you know, like we made it like 56 times faster, 60 times faster. We're gonna like start with reasonable benchmarks. So FP16, zero to negligible loss in performance, and like it's just one line change, which is like you just define torch d type as equals torch.float16, and it just works. So how does it fare? Oh, so there's a Colab notebook here. Let's see if it works. So all of this is under a repo called Optimize My Whisper. I should have come up with like better name, but you know, all of these are like Colab notebooks, so you can just click on open in Colab and it works. I ran it once so that like we have the results, but if you want right now, literally you can just click on it and just run it along. We're going to use very simple transformers API, so Hugging Face transformers, and we're going to use a very scientific IPython auto time to time each and every cell as to like how much seconds it takes. Let me quickly see if I can zoom in. Is it visible in the back? Okay. Maybe one more. Okay. Wait, get out of my sight. Okay, perfect. So the code is fairly simple. We define the torch D type over here. So you can see that it is torch.float16. And we use Colab T4 free GPU, right? And then we just initialize the model. The syntax is fairly straightforward for like any transformers model. And yeah, then we essentially we pass this model over to a pipeline, which initializes the model and initializes the D type, initializes which device does it need to go in, and then we pass a 10-minute sample to it. This, I put the recording online. It's a fairly sort of clean audio, 10-minute long, which talks about a meeting, something. You can listen to it or read the transcription below, and that's it. We pass it to the pipeline, and we time how much time does the pipeline take to parse the audio, and then of course run the model, right? And so this is our base case. So it takes about 1 minute and 2 seconds to transcribe 10 minutes of audio, right? So in terms of audio terms, your real time factor becomes 10x, meaning like the audio is 600 seconds, and it takes you roughly about 62 seconds to transcribe this, right? So our base case is already fairly fast for like real-time use cases. However, there are a lot of like architectural reasons why Whisper is just inherently slow because of its 30-second context window and so on. That's why like we ideally want it to be much more faster to be able to transcribe like word for word, right? And yeah, and that's the transcription. It's I think from a financial recording, but anyway, like the recording is CC BY, so do whatever you want to do with it. And okay, let's go back to the slides real quick. Slideshow. Right. So you can see. So the first one we get is 62 seconds, and now our goal is to try and sort of reduce this 62 seconds as much as possible, right? And let's see what we can do over here. All right, so the next one is sdpa or flash attention 2. So sdpa is scale.product attention. One thing that would be good to go back over here right now is to figure out why these models work. So the reason why these models work is because of this thing in the middle called cross attention, right? And since these are all like transformer type models, each encoder block is a transformer, right? And has in fact multiple layers of transformers in it. Each transformer block within this encoder block or the decoder block has multiple layers of self-attention. So there are two types of attention at play over here. One is self-attention, and the other is cross-attention, right? Both of these are at the best case, big O of n square complexity, meaning like you would have to go through like pretty much all the sequence and like all the so both the sequence sort of twice to be able to like each element in each array sort of goes and like multiplies with each other to be able to get the final output, right? And you cannot like just by the way it is, you cannot quite like optimize this process in the way transformers was made. Because of so many layers and so many times we perform this particular process, it is quite slow because of that. So what the PyTorch team and this fantastic researcher based in the US, Tree, did was create this library called Flash Attention. He created Flash Attention 1 last year, I think, or like a year and a half back, and Flash Attention 2 came out last year. These are both efficient ways of running the attention process, right? So what it does is it essentially gives you the same output as you would get from the standard attention, but faster. So how does it do that? Is number one, it parallelizes the attention computation over sequence length. So it would let's say you have 512 sequence length, then it would do like 256 on like one GPU or like tensor processing core, and the other one on the other tensor processing core, and so on. And second, it does so by even within those particular cores, like have multiple threads to sort of perform the same process, right? And the way it works is it reduces the overall interchange of communication between different cores, right? Lucky for us, we don't quite need to sort of implement the algorithm by ourselves because it is now upstreamed, as of like last month, it is upstreamed into PyTorch 2.3. Which means you can just use you can just define the attention type and it would default to that in the context manager. So sorry, keep forgetting that I have notebooks for this. So across all the notebooks, I follow the same structure. So essentially, you can just click on run all, and like it would give you like the same result pretty much all the time. And you can change like audios. You can use the same code for your own, experiments or commercially, non-commercially, however you want to use it. So you can see like everything is pretty much the same. We define the model. We load the model, and we pass it through the pipeline. We make one change in the model definition, which is we pass an explicit attention implementation as sdpa, right? if you have a newer GPU, you can pass flash attention over here. Because we're using Colab, we cannot quite replicate flash attention over here because flash attention only supports the latest sort of Ampere GPUs, which means it is restricted to A100s, H100s, A10Gs, and so on by NVIDIA. Just like some back of the hand math, if you use flash attention over normal attention, you get up to 2x to 2.5x benefits. So it's just out there for you to use in case you have a GPU which supports it. So we pass it through sdpa. This is like fairly old. And then we pass our sample, and we pass it through the pipeline, and we have saved a stonking 2 seconds. So yeah, like when I was making these slides, I was running on Colab with A100, and so the results were quite good. But then I ran them on a T4 this morning, and I was like, oh my god, this looks trash. But anyway, so this is what you have. You can change it tomorrow or like today, and just like run it on an A100. I just wanted to make sure that everyone can still run it, and the results are still scientifically correct. Well, scientifically. But okay, but nevertheless, we'll take the wins that we get. So we get 2 seconds of improvement, and yeah, let's go to the next one. So the next one over here is this really interesting concept, which was coined by Google, researchers at Google, called speculative decoding. Speculative decoding works on the idea that you can use a smaller network to do a first pass of whatever the input is, pass the output from the smaller network to the larger model, and then ask the larger model to verify whether these inputs are correct or not, right? What that means is that instead of so in terms of your computation cost, you offload the heavy lifting to the smaller model because it's it does the same distribution, like the initial tokens would always be the same, right? And you can use the larger model for essentially refining this entire process. And the way it works is that the assistant model generates a sequence of candidate tokens. So we'll actually see a quick video of this in a sec. And then the main model verifies these tokens through a forward pass and ensures the same outputs. Let's quickly look at how this would look like. Oh, this is a notebook, actually. 1 second. Typing with one hand is actually not as slow as I thought. All right, so is it visible in the back? Okay. So we have two models. They're essentially the same model, right? But one is a smaller model, like smaller as in terms of parameter size. One is a smaller model, and the other one is a big model, right? So the assistant essentially gets the audio, and it gives like the output, the quick brown sock jumps, whatever. Then the outputs from this. The outputs from this are passed to the main model, right? So this is essentially whatever token IDs would the assistant model pass, right? And so you can see that then the main model takes these inputs and it does one forward pass across all the token IDs to see if they're correct, right? And so in this case, at sock, it says that it should not be sock, it should be fox, right? And so what we do is we take all the sequences till the quick brown. So we've saved the computation for the quick brown for 3 tokens, and then we recompute from that place onward from the larger model, right? This seems like like an over-engineered solution, but this works fairly well in practice. And so bringing it all together, it would look something like this. Yeah, so like we say that that in the, sorry, the way this works is really baffling, but what we, like in the end, like what we get is from the main model is the final transcriptions, right? And I think this one. Yeah, so this is the whole process. You can see that then we give back the quick brown fox. Then we get the next tokens, which is fox jumps over the crazy dog, is what the assistant model created. And then we do another pass at it with the main model and so on, right? Now, the more times you do it, and the larger your sequence length is, the more you save, right? Just because, like, by and large, like there are certain patterns you can find in the audio, right? And so we just like replicate those all over as we transcribe. So that's the base premise of how speculative decoding works. So you can do this with Whisper, you can do this with Llama 3, you can do this with pretty much any open large language model or large model period, as long as you have a large model as well as the same sort of small model for it, right? At the end of the day, what you're doing is you're trying to offload as much as you can to a smaller model, and then using the larger model only to verify, right? And wherever it diverges, you essentially start generating from there. So over large sequences, this adds up quite a bit. Perfect. So, right. Oh, I went to the results very quickly. So again, we follow the same sort of structure. So we have the same collab notebook, unless in this, instead in this time, we set up an assistant model. This assistant model is the one that's going to do the heavy lifting for us. So this could be like a Whisper small model, this could be a Whisper medium checkpoint, could be anything, like just as long as it's not the same model, because then you're just doing the same computation twice. So any smaller model you can use as long as it's from the same distribution of the large model. Then you set up your primary model and you load it in the pipeline. Over here, there is essentially one more line change, which is you pass the assistant model over, and we take the same audio sample and we pass it through the pipeline, and we can see that this only took 37.9 seconds. So we essentially shaved off about, if my math is correct, 23.1 seconds. No, 22.1 seconds. Sorry. Like if you remember, before we were at 62 seconds, then we went to 60 seconds, and now we're at 37.9 seconds, right? So that's just by using like a smaller model, you save quite a lot, right? You do pay like, it increases your memory cost just by a tiny bit, right? However, this in the long run, just when you're optimizing for like real timeness, like it helps you so much. Cool. What can we do next? So we've already roughly gotten close to 50% of the time, right? So we've already roughly 2x'd this. Now, let's see what else can we do, right? So there's this, like, so if you have, let's say, 10 minutes of audio, the way typically any large language model or large model would work is it would take like 30 seconds, like, so in case of Whisper, it would take 30 seconds, or like, it would take the first 30 seconds of the audio, transcribe it, take the next 30 seconds of audio, transcribe it, take the next 30 seconds of audio, transcribe it, and then stitch all the transcriptions together. It is like just by definition is literally the most inefficient way that you can transcribe. So what we can do is we can employ some form of chunking, meaning we can take the audio, we can pre-chunk it, so we can just make 30-second chunks, and then we run parallel sort of model computation and parallelly transcribe these 30 seconds and stitch the transcription. Because we're essentially doing the same thing, but we're parallelizing this, right? Because why not? And the way we do it is just to make sure that the transcriptions are a bit more reliable, is we add some overlap. So like instead of doing 30-second chunks, we would do like 25-second, but with 5 seconds of overlap with the previous audio, so that we have some sense of reliability in terms of how the chunks do, right? In terms of how the overall transcription is, right? So a quick note over here. Chunking would almost always result in some degradation in performance, right? Because the model is not meant to do this. So you typically from our research, what we've found is you pay around 2% word error rate sort of penalty, but in most cases, as long as you want rough translations, it works brilliantly. So okay, let's see how chunking does. Again, one thing that I want to emphasize from this is the transformers code base. I mean, it does seem like I'm tooting my own horn because I work on the library, but I think it is a brilliant library if you want to research or if you want to use in production. All of our stuff is open source, so it's Apache 2.0 license. You can do whatever you want to do with them, and we're pretty much almost always very keen on collaborating on research efforts, and also in case you want to put stuff in production, we're happy to give you pointers. Just open an issue on GitHub and we'll help you out. Cool. So we do the same thing. We initialize the model. We put it on, oh, wait, this is a different notebook. OK, sorry. Now this is Distil. OK, sorry. Cool. So what we're going to do is we're just adding all the stuff. So we're now doing FP16 plus sdpa plus speculative decoding plus chunking on top of it, right? So we do necessary inputs. We initialize the model. We set up the assistant model same as last time. Set up the primary model, and we set up our pipeline. Then in the end, when we're asking the model to asking the pipeline to transcribe, we ask it to do it in 8 batches, meaning you essentially parallelize transcriptions across 8 batches, which means that you would have 8x the memory cost at this point, right? But because we're using a 16 GB VRAM in pretty much all sort of production use cases, you would have a lot of VRAM just to throw away, right? So in those cases, this helps you sort of efficiently optimize the model. Do I have more time? 10 minutes? OK, sounds good. Sorry, I was he had a banner and I did not see it, and I was like, do I need to go? But anyway, so we do it 8 times in parallel. And we get the time of 43.8 seconds. Why? We will answer this in a second. Stay tuned. OK, so we go back over here. And you can see that we are actually slower than speculative decoding. This is because speculative decoding was not meant for batched solutions, right? It's because in a batch solution, when you do forward pass, you do forward pass on the entire batch in one go. Now, in a speculative decoding setup, even if in one of the sort of inputs to the batch, there is a divergence on the first token, the entire batch is thrown away, and you perform the recomputation through the main model for the entire batch all over again. So we're essentially less efficient in this case. And in fact, having speculative decoding is worse off in this case. So I just wanted to I just put this here just as a mention that not everything is rosy, So do your own research and try it out on your own sort of audio. And yeah, let's see what else can we do. Cool. This is one of the last things that I'm going to be talking about. So this is Distil-whisper. So up until now, we were just using the base whisper model, and we were trying to optimize it. But can you go one step forward and just Distil-whisper? Meaning, can you create a smaller whisper model which is faster, but gives you the same outputs as Whisper. This is where Distil-whisper comes in. This is, we ran like a 6-month-long sort of research endeavor with Sanchit, huge shout out to him, who essentially took the Whisper model and then trained it, distilled it to create a smaller Whisper checkpoint called Distil-whisper, which essentially gives you the same output, but with less amount of memory required and more faster inherently. So it's a smaller Whisper model. What we do is instead of having 32 sort of decoder blocks, we just have 2 decoder blocks, and then we condition it on the main Whisper checkpoint. And we do it through, and we just like, while training, like I can talk about how we trained and so on, like outside, in case you're interested in that. All of the code for distilling Whisper is also open source, and we're happy to sort of help you distill Whisper in your own checkpoints, in your own languages and so on. Currently, it's English only. We're running some experiments to do multilingual Whisper distillation, but we'll see how it goes. And the results are within 0.5 word error rate. So, went to the results. Just don't look at the results. OK, so now what we're going to do is like the same thing. So we're going to, instead of using the main large Whisper checkpoint, we use the Distil-whisper checkpoint, right? And we do FP16, we do sdpa. We don't do speculative decoding because we realize that it doesn't work with chunking. So we're just going to do like Distil-whisper, FP16, sdpa, chunking. That's it. The same setup, you can see, like over here, we initialize with Distil-whisper. And we pass it into the pipeline. We pass the sample, the same sample as before. We pass it to the pipe, and voila. You can see that we did this in 17.2 seconds. And if you go back and see the slides, this is almost like 3x speed up just by using a smaller model, right? Of course, that makes sense because we're using a smaller model. But also, you can see that chunking over here works quite well, right? So we essentially managed to sort of do it in like half the time that it would take for like FP16, sdpa, and SD. There are a lot more. Sort of optimizations that you can do on top of it. Some of which I'm going to put over here. So if you want to go like even more faster, use flash attention 2. It's literally just changing the attention implementation from sdpa to FP2, or like flash underscore attn. Just literally just run it on any newer GPU. The same code would be like 2 to 3 times faster, right? T4 is, I don't know, like ancient, like, you know, probably my granddad used to use it. But next is quantization. So up until last year, we didn't have good quantization methods for Whisper models, just because you change modalities from audio to text. But now, thanks to whisper.cpp or faster Whisper, we have better quantization methods. So you can go all the way down from, so you saw before we were at FP32, then we went down to FP16. But with like whisper.cpp or faster Whisper, you can go down to Q4, so like 4 bits or like 8 bits. Pretty good overall. And something that I'm currently playing around with is using short context Whisper. So essentially, I'm just going to quickly open this for 1 hot second. So essentially, like using Whisper for just like small chunks for like 5 seconds at a time, and then like massively parallelize it. This is again something like we're just starting to look into, but this is like an interesting avenue to look around. OK, and so if you want to go more fast, here's there. If you want to chat more about the research ideas, catch me outside. Quick takeaways. At the very least, use sdpa or flash attention 2 if your environment allows. Like, please do that. For batch size equals 1 solutions, so the same as, for example, if you're using Grok or whatever, use speculative decoding. Pretty much always it will give you better results. For rough translation, where you don't care about precision, use chunking. Like you might like get slightly less reliable transcriptions, but as long as you care about the broad message, it works greatly. So in case like you have a setup wherein you pass the transcription to an LLM or something like that, in those cases, rough transcriptions do quite well. Oh, I just realized I have a typo. Anyway. For near real-time use cases, use short context, so like 5-second windows or 10-second windows. That's the research sort of direction that I was talking about. And Distil-whisper for use cases if possible, right? So we're like you can Distil-whisper with like less than 100 to sort of 400 hours of audio. So if you are sort of actually doing it for commercial use cases, I would say actually collect the data and then Distil-whisper. Last but not the least, don't trust this, verify it yourself. Thank you very much. You have been great.
Yeah. Thank you. Thank you very much. Hello. Yes, thank you. We have a lot of questions, so your talk is being very interesting. First one, do you see similar gains when using with MPS, so the Mac M1?
That's actually a very good question. We don't, because MPS, just by the way it is it's not as efficient. PyTorch does not support it as a first-class citizen. For MPS, for anyone who doesn't know, is the metal sort of kernels that you run on your Mac, especially like the latest series of Macs, and PyTorch is trying to do quite a lot with that, but it doesn't. In case you want to get similar gains on MPS or on a Mac, use whisper.cpp.
Thanks. We have one that is linked to another one, so I'm going to give you two. It's about speaker diarization. So I hope the question is not off topic. What do you think are the best model for speaker diarization?
Yeah.
And then the second one is also, how good is optimized whisper when combined with another model like PyNote?
Very good. Okay, so for diarization, currently in terms of open models, there are two good open models. So there is PyNote, of course. Huge shout out to Hervé if he's listening. Hervé is the author of PyNote. And the second one is from NVIDIA. In Nemo, it's called diarization or something like that. Both of them are really good. PyNote is slightly better. You can definitely combine it. In fact, there is, if you just go on GitHub and search insanely fast whisper, there is a GitHub repo by yours truly, which does the same thing. So in case you want to take it out for a spin, you can do that. Do note that this is like this part of the model is really not optimized, and this is something which is an active research that one of my colleagues is pursuing to see like how exactly can we get better results from it. It works well for English, but if you want to do it in Italian, if you want to do it in French, if you want to do it in any other non-English language, it just is crap. So, yeah.
Next question, what do you think are the most effective techniques to validate the quality of whisper in terms of word error rate?
Okay, just like literally just calculate word error rate. So what I typically do is whenever I'm trying out different optimizations, I would have a loop wherein I would have a lot of, I would have audios of varying audio quality. Right? So you can have very clean audio, you can have like audio that is recorded from microphone, you can have audio recorded from, I don't know, like 2-channel microphone. There's lots that you can do on that front. Just have your own vibe check sort of data set and run it all across and get like word error rate from it. There are like other more sophisticated ways. Like for example, you can calculate the signal to noise ratio of the audio and then correlate it with your word error rate. But it's too complex, and honestly, word error rate works quite well.
Thanks. So next question is there any explanation on why gains were smaller with SPDA with a low performance GPU?
Oh yeah, it's just that it is a low performing GPU. But like T4 is a very, very old GPU, right? I mean, it's I think like 4 to 5 years old. Through time, and I think if I'm not wrong, it still used like the CUDA driver it uses is 11.8 if I'm not wrong, or 11.9, and so massive gains that you see are in the way that CUDA drivers for more recent sort of Ampere type GPUs work. They like just by the way they work, they are more efficient in doing matrix multiplications. Plus, they do some sort of like operator fusing, meaning like you do a forward pass and like you can sort of fuse multiple operations together on those. That's why they're like a lot more faster as compared to a T4. But yeah, just like generally like T4 is slow. I would say like if you want to save on money, like I use T4s quite a lot. Like we use T4s quite a lot at Hugging Face for just like running inference for like quick things. It's great. It's very cheap. It's like 30 cents per hour or like 60 cents per hour. You can get it like if you shop around. You can get very cheap T4s. So it's good, but for production use cases, just use A100, H100s, or one of those.
Cool. Next one is about silences. So is Whisper itself well optimized for silences, or maybe we should cut the silences from the audio before transcribing it?
Yes, so Whisper is pretty much really bad when it comes to silences. What we recommend is to do voice activity detection, which is essentially whenever there is silence for more than a second, just chop it. Just chop your audio there, and then pass your audio to it. It is inefficient because, let's say you have a scenario wherein you chop it off at 2 seconds or 3 seconds. Whisper would still pad it up with, silence token all the way till 30 seconds. So you still like pay the padding cost in that way, but it is more reliable, if that makes sense.
The next one is, what about combining with approaches for making more reliable transcription, combining with wave-to-vec like WhisperX?
That is very interesting. So the WhisperX approach is very good. In fact, like what it does is it does like alignment of characters. So it takes a CTC model. A CTC model is something which takes 10 milliseconds of audio and maps it to a character, right? So they are less prone to hallucinations and so on. It works great. And WhisperX, I think, is a brilliant library, and I do recommend using it as well. I think they have issues with chunking more specifically, and that's why they don't like. That's why I personally prefer transformers. But in terms of like actually getting more reliable transcriptions, what I would recommend is to get transcriptions from any of these libraries and then pass it through a small LLM. So a small large language model. You can do like a 3B model or a 1.5B model or a 2B model and just ask the model with a very simple prompt. Is like, here is a transcription, here are the speaker IDs, here's blah, 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 blah. Please fix it. And it works because like you're using a large language model for just correcting English or like whichever language it is. So that works quite well. There is a paper from Google called Diarization LM which does the same thing. And if you wait till next week, then we're going to release something similar as well.
Cool. So unfortunately, we don't have any more time for other questions.
Okay.
But thank you very much. That was awesome.
Thank you very much. You've been lovely.